Assalamu alaikum. Welcome to my video series on data science. Today we will be exploring one more data transformation technique, which is dimensionality reduction. In this session, we will explore key concepts like feature selection, feature extraction, and then we'll kick off our discussion of principal component analysis with a numerical example and hands-on Python implementation. So let's get started. Dimensionality is a curse. Let's find out why. The curse of dimensionality refers to the challenges and inefficiencies that arise when working with high dimensional data. As the number of features or dimension increases, the volume of data space expands exponentially, making it sparse. This sparsity leads to issues such as overfitting, increased computational complexity, and difficulties in identifying the meaningful patterns in the data. Dimensionality reduction is a process of reducing the number of variables or features in a dataset to simplify the analysis and modeling while retaining the critical information of the data. There are two types of dimensionality reduction. One is called feature selection and the other one is called feature extraction. Feature selection involves identifying and selecting the most relevant features from the original dataset, reducing the dimensionality without altering the data. Feature extraction transforms the data into a new feature space, combining or projecting the original features into a lower dimensional representation while preserving important information. In feature extraction process, the original values of the data are not retained. So in this video, we will focus on feature extraction. Here are some common feature extraction methods: principal component analysis, linear discriminant analysis, independent component analysis, single value decomposition, TSNE, and autoencoders. In this video, we will be focusing on principal component analysis, that is PCA. Principal component analysis is a widely used technique for dimensionality reduction. It transforms the original features of the dataset into a new set of uncorrelated variables called principal components, which captures the maximum variance in the data. The first principal component explains the largest variance, and each subsequent component accounts for the remaining variance while being orthogonal to the previous components. Let's understand it by an example. Let's think of this pole as our dataset, and the two different images represents how we view the data from different perspectives. Right now, we see the pole from two angles, one from the side and the other from top. This is exactly what PCA does. It looks for the best views or perspectives of our data, called principal components. These components highlights the most important features or direction of variance in the data. Just like how pole looks different from each angle, PCA projects our data into new axes or directions, capturing the essence of the data while simplifying it. Now let's discuss how PCA works. So here are the key steps in principal component analysis. First, we standardize the data, then we compute the covariance matrix. Then we compute the eigenvalues and eigenvectors. We sort the eigenvalues and eigenvectors in descending order and select the top k principal components. Using the top k principal components, we project the data into a new feature space. Let's solve a numerical example using principal component analysis. Here we have given a dataset that contains two features, age and height. And we will transform this data to a single dimension. Since the PCA is affected by the scale of variables, the step 1 is to standardize the data. This is done using the z-score formula by subtracting the mean from each point and then dividing by the standard deviation. We have discussed this in detail in the previous video. You may find some examples where the data is not completely standardized, but it is just mean centered by subtracting the mean from each feature. It is used when the feature scales have less variation. After standardizing the data, we will compute the covariance matrix. You can find more about covariance in my correlation analysis video. Next, we will compute the eigenvalues and eigenvectors. To compute eigenvalues, we will use this equation. Determinant of A minus lambda is equals to 0. Here A is the covariance matrix and I is the identity matrix. After multiplying the lambda with the identity matrix, we will subtract it from the covariance matrix. So now we will take the determinant of this matrix using this formula. So after taking the determinant, we will get this equation, and after simplifying it, we will get this equation. We can easily calculate the coefficients of this equation from the calculator. So the first coefficient came out to be 2.59 and the next one 0.07. And actually these are our eigenvalues. So we will name them lambda 1 and lambda 2. We can calculate the explained variance ratio for each eigenvalue as follows. It indicates that a single principal component is able to capture the 97% of the variance in the data alone. Now it's time to calculate the eigenvectors using the equation AV equals to lambda V and then rearranging it. Here V is a vector V1, V2. We will substitute the first lambda value into this equation. After simplifying it, we will get these two equations. Rearranging the equation 1 for V1 and we will get this result. V1 equals to 1 times V2. So the eigenvector corresponding to the eigenvalue can be represented as 1, 1. Similarly, we will compute the eigenvector for the second value of lambda, that is 0.076, and we will get 1 minus 1. Now we have sorted the eigenvalues and their corresponding eigenvectors in descending order. We will select top k principal component. In this case, we have only two features and we want to reduce it into one. So we will select the highest value of lambda, that is 0.259, and its corresponding eigenvector. So before projecting the data to a new feature space, first we need to normalize the eigenvector. First we calculate the norm or the magnitude of the vector using this formula. Then we divide each value of our eigenvector by the norm. Finally, we will get a normalized eigenvector that will be used to transform the feature space. To transform the data, we will take our standardized data and then we will multiply this by our eigenvector. As we can see, the data has been reduced to a single dimension. So this is the basic principle on which principal component analysis works. Now let's quickly find out how can we apply principal component analysis using Python. Here I am using a V dataset that contains several features like area, parameter, compactness and so on. So the data looks something like this. If we see the pair plot, we can see that a lot of independent variables have a significant correlations with each other. So we can reduce its dimensionality using PCA. So first we will select only the independent variables and we will exclude the dependent variable from this data. We will import PCA from Scikit-learn library. Let's reduce the dimensionality to 3. We will call fit transform method and pass our independent variables to this function. As we can see that the first principal component explains 82% of the variance in the data and the subsequent explains the remaining. Here we can see our transform data. To use the data, we will create a new data frame and we will give these columns some names like principal component 1, 2 and 3, and then we will combine the target variable with this data. Now in the pair plot we can see that the independent variables are not correlated. You can also explore other dimensionality reduction algorithms like SVD, LDA and isomap. If you found this video helpful, don't forget to like, share and subscribe for more videos on data science and AI. See you next time.